All right, in class we talked about electron configurations, the full electron configuration, as well as the noble gas abbreviated configuration for different elements. Today we're going to look at something called valence configurations, which are related to that, and then we'll talk about orbital diagrams as well. So we remember that the periodic table is divided up into blocks, an S block, a P block, a D block, and an F block. And we know that the Aufbau principle tells us to fill up the energy levels, the sublevels, from the lowest sublevel energy to the highest. So we start with the 1s, then we move to the 2s, to the 2p, the 3s, and 3p. Then we go to 4s, 3d, 4p, etc. So that's what we talked about in an earlier video. So let's just quickly check your understanding of that, because we need to take where we left off and move from there. So can you draw for me, pause the video and try this yourself, can you draw me the full electron configuration for the following element? So actually, let's do a couple of them. So give me the full electron configuration for silicon, and then also give me the full configuration for, how about gallium? Okay, silicon is element number 14, gallium is element number 31. So you can pause the video and see if you can write those out. So for silicon, you would start with 1s and 1s2. It's got 2 electrons in the 1s sublevel. On my periodic table, I'm at helium right now. 2s2 and 2p6. It's got 2 electrons in the 2s sublevel, 6 electrons in the 2p sublevel. We're at neon right now, and we're working our way through to silicon. So after 2p6 comes 3s2, we're at magnesium, and then 3p, the silicon element, is in the third row of the p block, so it's 3p2 because it's the second element in. So there's silicon's full configuration. For gallium 1s2, we're at helium, 2s2 and 2p6, we're at neon on the periodic table, 3s2, 3p6, now I'm at argon, and then entering into the fourth row of the periodic table, 4s2, there's calcium, 3d, remember that the D block, the energy level is 1 lower than the row number on the periodic table. So in row 4, it's going to be 3D. And 3D10 takes us to zinc. And then we're back to the P block, so we go back to 4P. And gallium is the first element, 4P1. So there's the full electron configuration for 2 different elements. Now, notice within those full configurations, you have different energy levels. For silicon, we have energy level 1, we have energy level 2, and then we have energy level, pick a different color here, we have energy level 3. Those are the 3 energy levels in silicon. And if we do the same thing for gallium, we have energy level 1, we have energy level 2, and then we have energy level 3. Now energy level 3, notice if we're careful here, there's energy level 3 here, but there's also energy level 3 over there. And then we have energy level 4, which is here. So there's energy level 4. So what we're going to do is write what's called the valence configuration. Valence configuration. If you remember from grade 11 chemistry, valence electrons in the Bohr diagram were the electrons that are in the highest energy level within the atom. Okay, so valence electrons, if you don't know that, you'll want to write it down. Valence electrons are the electrons that are in the highest energy level within the atom. So if we're looking for the valence configuration, we want to write the part of the full configuration that is in the highest energy level. So when you look at silicon, if you're wanting to write its valence configuration, you notice that level 3 is the highest energy level for silicon, right? So what we're going to do is simply write down the part of its configuration that's in level 3. So for silicon, it would be 3s2 and 3p2. Those are the two pieces that are in level 3, the highest principal energy level for silicon. Do the same thing for gallium, but notice that for gallium, the highest energy level, the valence level, is level 4, right? It's got level 1, level 2, level 3, and level 4. So gallium's valence level is level 4. So you'll include only the parts that are on level 4, the valence level. So for gallium, 4s2 and 4p1 would be the valence configuration of that element. All right, now see if you can go the other way around. I'm going to give you a valence configuration, and you tell me which element this is. All right, so I'm going to glance at a periodic table here. How about, well, let's say this. So you give me the valence, so you identify which element has the following valence configurations. Okay, so there's 2 of them. So tell me which element has a valence configuration of 5s2, 5p5, and then which one is 6s2, the valence configuration. So it's actually easier than you might think. So 5s2 and 5p5, all I really need to do is notice the 5p5. So I go to my periodic table, I'm looking in the 5th row and in the p block. So 1, 2, 3, 4, 5. So we're looking in this section that I've just highlighted in green. There's the 5p section. And we said 5p5. So the 5th element in would be iodine, right? Element 53. So this guy, this valence configuration belongs to iodine. Do the same thing for 6s2. So you glance at a periodic table, 6s2, so you're in the 6th row. So go down to the 6th row. You're in the s block. So the S block are the first 2 columns, and 6s2, that's the 2nd element in there. So 6s2, that's going to be barium, right? In the 6th row, 1, 2, 3, 4, 5, 6, the 2nd element of the S block, that's barium. So we come over here and say this valence configuration belongs to barium. So if you're given an element, you should be able to write its valence configuration. If you're given a valence configuration, you should be able to identify the element. So now we know how to write full configurations. We know how to write noble gas abbreviated configurations from an earlier lesson, the earlier video. And now we know valence configurations. So the last thing we want to look at is called orbital diagrams. Orbital diagrams. We've actually almost seen these already. If you go back to the graph on the right-hand side here, let me erase my highlighting. This energy graph on the right-hand side is almost what we would draw as an orbital diagram. Each of the boxes in the diagram was an orbital, and earlier we were putting electrons in those boxes, but we were representing the electrons with numbers. I put 1 electron or 2 electrons by writing the number 1 or the number 2 in the boxes. What we're going to do instead now is we're still going to use boxes, but now we're going to use arrows to represent electrons. So boxes, these are going to represent orbitals, and we're going to have arrows that represent electrons in the boxes or in the orbitals, right? So it's not as hard as you might think. Let's give it a try. So I'm going to take carbon as the first element that we'll look at, just randomly picked that. Think about what carbon's electron configuration is. 1s2, 2s2, and 2p2. So for carbon, we're going to need one box, and we'll write 1s above that. So there's the 1s sublevel. Then we have another box, there's the 2s sublevel. And then then comes 2p, and remember the 2p sublevel always has 3 boxes. So I'm going to write 3 of them. There's 3 orbitals in the p sublevel. So, whoops, this is 2p. So each box is an orbital, right? The 2p sublevel has 3 orbitals, the px, the py, the pz on the x, y, and z axes. So we put 3 boxes. Now, the configuration was 1s2. So look what I'm going to do. I'm going to draw a half arrow pointing up. That is 1 electron. Now, if you recall Pauli's exclusion principle, let me just remind us. Pauli's exclusion principle, I'm having trouble writing here. Exclusion principle. It actually had 2 parts, right? We said earlier that it tells us each orbital holds a maximum of 2 electrons. That's the part we talked about in our earlier video. But remember, there's more to it than that. With opposite spins, right? So you remember we said in our notes that we envision that an electron is like a particle. We know it's more complicated than that. It has wave properties as well. But let's just imagine it for a moment as a particle. We imagine that this particle is spinning. So it's spinning. In this case, it's spinning to the right. As it spins, a negatively charged particle, it creates a magnetic field. Now, I'm going to guess, because I didn't look this up, but a negative particle spinning one way creates a magnetic field north-south. I may have that backwards. And then when it spins the opposite way, it has the magnetic field reversed, so south-north. Every electron has a magnetic field, so we imagine that magnetic field is created by a spinning electron. Pauli's principle says that each orbital holds 2 electrons, but they must have opposite spins, so their magnetic fields will cancel out. When one of them spins one way, the other electron in that orbital has to spin the opposite way. So to show that in the orbital diagram, if an arrow points up, it means the electron is spinning one way. So the next electron has to have opposite spin. So I'm going to draw an arrow pointing down. So 1 up, the electron spinning in one direction. 1 down, the other electron is spinning in the opposite direction. Now we've obeyed Pauli's principle. That orbital has 2 electrons with opposite spins. The 2s orbital has 2 electrons with opposite spins. And now something a little bit tricky. For carbon, it ends in 2p2. So where should I put these 2 electrons? Do I put them in the same orbital? Do I put them like the others in just one box? Or do I put them in separate boxes? The answer is we put them in separate boxes. So we're going to put 1 electron there, and in the next box, we're going to put another electron there. All right, so that's called Hund's rule. Hund's rule. What it says is if you're filling equal energy orbitals, which is what we're doing right there in the 2p sublevel, keep your electrons unpaired as long as possible. So keep electrons unpaired as long as possible in a sublevel. Okay, so we're filling up the 2p sublevel. We're filling 3 equal energy orbitals. We need to keep the electrons unpaired as long as possible. One way to understand why this is because electrons are negatively charged. If you put them in the same box, they would repel each other when there's 2 other boxes with equal energy available. So if you're able to put them in an empty box with the same energy, that's what you should do. It minimizes the repulsion between the electrons. All right, so there is the orbital diagram for carbon. Right, that's it. Let's do another one. So looking up at a periodic table here, how about we try sulfur? Let's do sulfur's orbital diagram. Okay, so if you have your own periodic table, find sulfur. It's underneath oxygen on your periodic table. Be sure you're looking at that. And then imagine what its electron configuration would be. Sulfur is going to need 1s, and it's going to have 2 electrons there, so 1s2. Then it has 2s. It's going to have 2 electrons here, 2s2. Then it's going to have 2p, 3 boxes because there's 3 orbitals. And now watch, let's obey Hund's rule. It's going to have 6 electrons here, but look how I'm going to put them. 1, 2, 3. Keep them separate as long as possible. That's what Hund's rule said. Keep the electrons unpaired as long as possible in a sublevel. But now we need 3 more electrons to go in. We don't have a choice. So the 4th, the 5th, and the 6th will have to be paired up. All right? Then comes 3s. We put another box with 2 electrons, opposite spin. And then comes 3p, where we have 3 more boxes, right? Now, what does sulfur end in with its configuration? It's going to end in 3p4. So let's obey Hund's rule. We're going to keep the electrons unpaired as long as possible. Whoops, I'm using my eraser there. Grab my pen. 1, 2, 3. So we have 3 unpaired electrons there. And now there's my 4th one. All right, so 1, 2, 3, and then a 4th one. So notice in sulfur, we end up with 2 unpaired electrons. You should note that. There are 2 unpaired electrons. Looking back at carbon, up above, carbon also has 2 unpaired electrons. Whenever an atom has unpaired electrons, whether it's 1 or 2 or 3 or 4, if it has unpaired electrons, we say that it is paramagnetic. Okay, so paramagnetic, you should write down what it means. This is an atom that has unpaired electrons. It doesn't matter how many, but if it has any unpaired electrons, it will be paramagnetic. All right, so looking back at a periodic table, let's try another example. How about, let's try chromium. Can you draw chromium's orbital diagram? You're going to need to look at your own periodic table. Chromium is element number 24. Okay, so element number 24, chromium. It's got a big orbital diagram. Okay, so pause the video and see if you can try it yourself. So 1s2, 2s2. Be sure you're putting the boxes and the labels above, okay? Then comes 2p6. 6. And we're going to obey Hund's rule. 1, 2, 3, 4, 5, 6. Keep the electrons unpaired as long as you can, then pair them up. Then comes 3s, 2. Then comes 3p, and we're going to obey Hund's rule again. 1, 2, 3, 4, 5, 6, 3p6. Then, now let's see if I caught you. Did you remember that in our earlier notes, we said chromium is an exception to the off-bow principle? Did you remember that? Chromium is an exception. So where you might have thought it should be 4s2 and 3d4, in fact, it's 4s1. So we just put one electron there. And then 3d5. So one of our 4s electrons has jumped from the 4s box into the 3d boxes. So instead of 4 arrows in the 3d, we get 5. So 1, 2, 3, 4, 5. Obeying Hund's rule, keeping them unpaired as long as possible. So when you look at chromium, notice that there are a total of 6 unpaired electrons. And if you have any unpaired electrons, you are paramagnetic. So chromium is paramagnetic, highly paramagnetic. It has a lot of unpaired electrons. Okay, let's try one last example. How about argon? Give me the orbital diagram for argon, which is element number 18. Pause the video and see if you can do that yourself. So argon 1s2, 2s2, 2p, 3 boxes, and 2p6. I'm at neon now on my periodic table. Then 3s2, and then 3p, 3 boxes, and 3p6. So 1, 2, 3, 4, 5, 6. There is argon's orbital diagram. Now notice it has no unpaired electrons. There are no unpaired electrons. Well, if there's a special word for when you do have unpaired electrons, that was paramagnetic. There's a special word when you don't have any. It's called diamagnetic. So we say, therefore, it is diamagnetic. When you have no unpaired electrons, you are diamagnetic. Okay? Now, before I leave you, let me just show you orbital diagrams. I've been drawing them with boxes and arrows. Some people draw them, or some textbooks will draw them a little bit different, but you'll see it's the same thing. Instead of a box, they might put a line, and they might say 1s, and then they'll put 2 arrows, 1s2. Then they'll put another line, 2s2. And they'll put 3 lines side by side. There's your 2p. Notice you can tell that the 2 p's go together because they're close together. And then they'll put 3s, a little gap in between, 3s2. And then they'll leave a gap and put 1, 2, 3 close together. There's 3p, 1, 2, 3, 4, 5, 6. So it's the same idea as the boxes, but they're just putting lines and they put the labels underneath usually. Some people don't use boxes or lines, and they don't use arrows. They'll do this instead. They'll draw a circle, and they'll say that's 1s. And then instead of arrows, they'll do this. 1 electron, 2 electrons. There's 1s2. Then they'll draw another circle. There's 2s, 1 electron, second electron. There's 2s2. And then 3 circles very close together. There's 2p. Hund's rule, 1, 2, 3, and then 4, 5, 6 electrons. There's 2p6. And then 1 circle, 3s, 3s2, 3 circles close together, there's 3p, and Hund's rule, 1, 2, 3, 4, 5, 6. So that's just another way of showing an orbital diagram. You should be familiar with all of them. You might see them on a test or something like that. When I draw them, I almost always use boxes with arrows, but you'll see these other representations in textbooks or on the internet as well. Just recognize they mean the same thing. All right, so you can now draw full electron configurations for elements. You can draw noble gas abbreviated configurations where you start with the last noble gas, you put its symbol in brackets, and then you add on the new things after that. You can do a valence configuration, which is the electron configuration, but only the highest energy level part, the valence level. And now you can also do orbital diagrams, where the electron configuration is translated into these boxes with arrows, and you understand what paramagnetic means. The atom has unpaired electrons, and diamagnetic, the electron has no unpaired electrons. All right, so that's pretty much the end of the quantum model of the atom. Now we just have to practice it with some homework problems. So if you have some questions, specific questions, you can ask me in our class Zoom meeting, or you can even post the question on Google Classroom, and I will try to respond it there. If you put the question on Google Classroom, try not to do a private question. Make it a public question so everybody can see it and everybody can see my answer. All right, so good luck.